All right, everyone, welcome back. So are there any questions about correlation or linear regression as a process before we start working through another example? Again, this is one of those things that can be done by hand, and I do want you to understand what that process looks like, but in practice it's far easier to do it with a calculator. And again, be careful about what kinds of conclusions you can draw. You can conclude things from the average, from the slope on average, and from the y-intercept in some situations, but you need to ask yourself, first of all, whether the y-intercept value makes sense, and also whether it makes sense to consider what happens when x equals 0. Okay. So, this example, as I said, is one of my favorites because it is real-world data, and it does give us some actually interesting information. And if you're a sports fan, you might find the conclusions you can draw from it to be of interest. So, hopefully some of you know who Hank Aaron is. I was actually disappointed the last time I asked this in front of a class. A number of people did not know. Hank Aaron was a famous baseball player, a trailblazer in many ways. He broke Babe Ruth's home run record and then held the record for quite a few years until Barry Bonds broke his record. Some things to be said about that as well, but I'm not going to get into that today. But Hank Aaron dealt with a lot of things. He played for the Braves in Atlanta and was not treated well as a black individual who broke Babe Ruth's record. Obviously a white individual, and he dealt with a lot of racism among other things, and had a remarkably long and productive career in all of those circumstances. Was very active in civil rights work then and much later especially. Amazing individual. Unfortunately, he died, I believe, a year, maybe 2 years ago at this point. But an amazing person. I'm going to leave it at that. This information is the number of home runs that he hit at the end of each of his first 20 seasons in the league. Now you'll notice here in his first season he had 13 home runs. In his second, he had a total of 40. In his third, he had a total of 66, and so on. So by the end of his 20th season, he had hit 713 total home runs. And you may or may not know this, but Babe Ruth's record that he held until, 74, I guess, was 714 home runs. And in fact, it's important enough that the numbers 714 and 715, so 714 was Babe Ruth's record, and the 715th home run that Hank Aaron hit was the one that broke that record. Those are called Ruth-Aaron numbers, and my advisor's done some research on them because they have some very unique numerical properties. If you Google that, Ruth-Aaron numbers, you'll find some interesting stuff. I think something like the sum of the factors of the first one is the second one, and vice versa. And there's something else about their products. Anyway, it's really kind of an interesting property that very few numbers have, but those are the first two. All right, so what might I want to do with this? Well, I can certainly see that over time he's hitting more home runs, which makes sense. But is he hitting home runs at a steady rate? That is, am I seeing a linear relationship when I do this? Well, one thing I could do is I could try to plot the 20 years worth of data here as a scatter plot, and then build a best fit line, a linear regression line, to make predictions and understand the relationship that I'm seeing here. So I'm going to show you how to do that on Desmos, and then I'm also going to show you how to do that on Vasterstats, the other program that I was going to show you today. So let's do that here first. If I'm going to do this on Desmos, then what I will want to do is to input all of this data into a table. Now I know the x values here are just the season numbers, so that's pretty easy to remember. I'm just going to type in the information for the home run totals. 13, 40, 66, and 110. 13, 40, 66, and 110. It's going to break when I go past the 6 data points, that's okay. 140, 179, 219. Okay. 253, 298, 342. 342. All right. 366, 398. 442, 41. 510, 554. 592, 639. And 673, 713. Hopefully I typed that all in correctly. This. I should have just started from scratch rather than trying to rebuild it into the one I already had. Did I really just do that? Now, I can do this. And it should be okay. All right. So let's see if this will let me do it. No, it won't. Oh my goodness. Am I really going to have to? Okay. You know what? I'm not going to do it here. Desmos would allow me to build the best fit line there, but I'm just going to jump straight over to Vassar stats. So by the way, let's start here at the main site. You go to VassarStats.net, and I'll provide the link to that for you in the slides here as well. It gives you a number of other calculators. Again, unfortunately, I can't suggest using it for hypothesis testing and things like that we've already done because I've run into the trouble that it does not give us enough decimal places. It'll give you a p-value to 3 decimal places and a test statistic to 2, and unfortunately the homeworks and the exams expect more decimal places than that. The numbers are correct to that number of decimal places, so it's obviously not doing things incorrectly, just it doesn't give you enough information to use it there. But if you click on correlation and regression, this one will actually give you a number of other features that Bogner's calculators do not. That's part of why we're using this, is it does allow us to do some things that we can't do there. But the cost is that there's a lot more to wade through to get there. We're going to be using this for correlation and regression, so if you click on that, we're just doing a basic correlation and regression situation. This would be producing that table of correlations I was talking about. If I want to input my data from a large data set in a spreadsheet, I can use this data import version. I recommend, since we'll be dealing with small data sets, just using the direct entry version. So that's what I'm going to use here. It asks me up front, how many values am I inputting? And in this case, I'm inputting 20. Now, I guess I'm going to have to type those in again. What were those numbers? 40, 66, and 110. And 140, 179, 219. So let's do it this way. Yeah. There we go. Alright, 179, 219, 253, 298, 342, 366, 398, 442, 41, 510, 554, 592, 639, 673, and 713. Alright, good. That's the 20 values. I ended up at 20. And since I'm using my season number as inputs, I don't even need to look. I know what those are. Doesn't help that men right. Ugh. Alright. So now that I have my data in, I would recommend checking those. Yep, I think those are all correct. Alright, and click Calculate. And you'll notice it computes the residuals for each of those values. Alright, you'll notice these residuals tell you how far away from the predicted value they are. And notice that the residuals are very large here and large here. Okay, so there's some interesting things happening here. Here x equals 1 and here x equals 20, which we'll talk about again in a moment. It computes, well, you can use these calculations to actually more effectively calculate that correlation coefficient. I'm not going to worry about the details on that. But here's the average x value and the average y value. And so that point, with this x and this y, will be a point on the graph of the best fit line. Looks like our r here is close enough to 1 that this calculator can't tell the difference. And our y-intercept is negative 39.84, and our slope is 37.262. So let's check, does that line up with what I found? Okay. I'll show you how to do that in a second. Negative 39.847 plus 37.262. There we go. So that is the correct best fit line. The best fit line looks like this. 37.262x plus negative 39.847. So let's think about what those two things mean, first of all. What does the 37.262 actually mean? Is that the slope? Is that the y-intercept? And then what does it mean from there?
The y-intercept.
So actually, this is the coefficient of x. So that 37.262 is going to be the slope. Now, what are its units? When you compute the slope, remember it's rise over run, so it's the y values divided by the x values. What are my y values here? Like 40, what is 40 what?
Home runs.
Right. The units there are home runs. So the y values are measured in home runs, and the x values are measured in
time in years.
Yeah, years or seasons, whichever way you want to look at it. Okay. So if I look at the units for slope, it will be units of y per unit of x. Here that would be home runs per season, or home runs per year. Okay. So if I use that, this implies 37.262 home runs per year. That's the average number of home runs we'd expect him to hit in a season, based on this 20 seasons worth of data. Now, if you know anything about baseball, especially at that time, that's a remarkable number. That's a good year for most players. It's a very good year for most players. It's a great year as an average over 20 whole seasons, which is longer than most baseball players' careers. So that's interesting. The 37.262 gives us an average number of home runs hit per year. What about this negative 39.847? Now that's the y-intercept. So what does that stand for? How do we interpret a y-intercept? Alright, so remember that the y-intercept is always found where x equals 0. So in this case, this negative 39.847, that's my predicted y value when x equals 0. So I predict in season 0, that is before he's started in the majors, that he has negative 39.85 home runs. So in short, that's nonsense. Okay? That negative 40 is kind of like an adjustment factor for the model itself. It gives us a prediction in year 0 that makes no sense whatsoever. In fact, it gives us a prediction in year 1 that makes no sense whatsoever, because at the end of year 1, he had 13 home runs. If I subtract the negative 39.847, that's going to make a negative number of home runs, negative 26 home runs. Again, doesn't make any sense, right? But that's just to make the model line up with what I see over the long run. Okay? Essentially, he hit fewer home runs in his first 2 seasons than he hit on average for the rest of his career. And so that's why I'm seeing some odd behavior there. And we also saw that when we looked at the residuals. We saw that the residuals were pretty high for the first 2. The line over-predicted the number of home runs he would have. But pretty quickly, it turns negative, meaning he's hitting more home runs than would be predicted at that point. So he started hitting a lot of home runs. How many home runs did he hit here? Let's see, 27, 26. Wow. 44, 30, 39, 40, 44. Okay. Or no, excuse me, is it 44? No, it's 34. Sorry. Tired. All right. I'm going to stop making those predictions, but we can see that he's hitting a fair number of home runs every year, and he's being pretty consistent with that. All right. So that's average per season comes directly from looking at the slope. Right? The slope tells us units of y per unit of x on average, and in this case, it's telling us that on average he's hitting about 37.3 home runs per season, okay, at least based on this model. It's not exactly right because this y-intercept would have to be 0 for that to be exactly the average, but it's pretty darn close. It tells us essentially per season what we would expect to happen as he goes one more season if he continues that level of productivity. And then we see this many home runs hit on average. All right, now that data was the first 20 seasons of his career. Okay, he actually had a 23-season career. So he played for 3 more years, and that's why, of course, he ended season 20 on 713, 1 below Ruth's record. And he played for 3 more years. Of course, he did break that record. He ended up with 755 total. If we use this model, we can make a prediction for how many home runs he'll have after his 21st season, which is the 1974 year, his 22nd season, and his 23rd season. And what would those values be? Here, I'll go back to decimals. Just clear all this stuff out because that's not necessary at this point. I'm going to create a function that does exactly what that model told me. Minus 39.847. And then I'm going to ask myself, what would my model predict in 1974, his 21st season? Well, that would predict about 743 home runs. All I did there was I plugged 21 in for the season number to find the next season's predicted total. That's my y-hat there. What about after 75? This model predicts 780 home runs. And in his last season, when he retired, this model predicts that he hit 817. Okay. Now, as I said, the number of home runs he actually hit was not 817 by the end of his career. It was actually 755. So why do you think that the model would predict 817 when he actually hit 755? What's going on here?
It's assuming that he's not getting older or any other factors.
Sure.
Health.
This model was built on the first 20 seasons of a remarkable Major League Baseball career. And he played 3 more years, which again were still good years by most measures. But you can't expect that in years 21, 22, and 23 he's going to do the same as he did on average through the first 20 years. That is, the trend that we see in those first 20 seasons includes a lot of great years in his prime. We wouldn't necessarily expect him to continue hitting home runs at the same rate in his last 3 seasons in the league, especially after 20 seasons already under his belt. So we don't expect him to continue hitting 37-plus home runs on average per year, as the model would predict. We'd expect him to hit a few less because, well, he's getting older, right? Still had some great years, still added to those home run totals, just not as much as this model might predict. And so that's exactly what we're looking for there. All right, now I have a couple other things I did want to point out. Keep in mind these residuals, when they're calculated as the difference between the observed Y value and the predicted Y value. And Desmos shows that to you graphically and creates a list. Stats doesn't show it to you graphically, but does create the list of residuals here. And those residuals tell you, compared to the predicted value, how did your actual value show up. So for instance here, my predicted value is lower than 13. And the reason for that is because my predicted value incorporates this, where is it? Negative y-intercept. And so in year 1, 37 minus 39.8, my predicted value is negative 2 home runs. And he obviously did better than negative 2, as I would hope. And so I have a positive residual. The observed value here of 13 is about 15.5 above what the model predicted. Here, my observed value of 40 is about 5.3 above what my model predicted. And then here in year 3, I'm about 6 below. Okay? So my model predicts more. Here, I observed more. Here, my model predicts more. My model predicts more, and so on. So it tells you how the actual observations match up with the model's predictions as you look at each of these individual values. You can also look, is there a trend here? Like, can I see that he's always above at the beginning and then always below at the end, or anything like that, okay? If I were to include those last 3 seasons worth of data, then I would find that the residuals were negative for those last 3 seasons worth of data, and that's why he ended up with fewer home runs than the model predicted, okay? If I look at the actual residuals here, this positive 8 says that he hit 8 more home runs by the end of this 18th year than this model would have predicted. And my guess is that's because he probably had a good year, since he started below the prediction at the end of year 17 and finished above the prediction by the end of year 18. He must have hit more than the 37 average that he had most of the time. So what did he actually hit? He hit 47 between years 17 and 18. And so obviously that means he ended up ahead of the prediction when he started off behind. And by the end of this one, he was not quite as far ahead, but still ahead. So I think he probably hit a little less than 37. He hit 34. Okay, so he's still ahead of the predicted value. And here he hit 40 home runs. So he increased how far away from the predicted value he happens to be. And that's why the residual is even higher. Okay. So those residuals tell you how far away his actual totals were from what this model predicts. And if we want to check what's called the equal variance assumption, essentially what we're looking for there is, as I use this model, as I move from left to right, am I finding that the variance that I see from the model is the same? Is it consistent? I can usually do a plot of the residuals to check that. So if this is my plot of residuals, they should be centered around 0. That should be the average residual, right? That's what it means for a best fit model. Some of them will be above, some of them will be below, and what I want is I want to see that they're equally distributed on both sides and that there's no clear trend as I move from left to right. Okay? Now, if you are building a sampling distribution for this, it turns out the standard deviation of the residuals can be computed by this formula. You add up the squares of those residuals and divide it by n minus 2. That gives you a variance for the residuals, and then of course the square root will give you the the standard deviation. And we'd like to see that set of residuals has a roughly normal distribution. Okay, that's really the best situation to be in. If we have that, we can actually use some statistics about the distribution of those residuals to then test whether our correlation coefficient is significant. Okay, and I'll get to that in a moment, but for now, let's talk about also R squared. So when you look at the values it gives us here, it gives us not just R, but also R squared. And unfortunately here, my R happened to be almost perfect. It really should be 0.99 something, and I think Desmos gives me more decimal places again, so it would show something a little bit better than this. R squared is simply taking R and multiplying it by itself. Now, if I think about what that does, R is something between -1 and +1. And if it's closer to one of the extremes, then when I multiply it by itself, the negative sign is going to be eliminated. I'll always get something that's larger on the positive side. Okay? It'll be between 0 and 1. It will only be equal to 1 if R is +1 or -1. If it's a perfect fit line, I'll get R squared equals 1. If it's a terrible fit, it's close to 0, then I'll get R squared that's even closer to 0. It's R times itself. If R is close to 0, then R times itself is even closer to 0. And the worst it could be is actually equal to 0, in which case R squared equals 0. So R squared is always between 0 and 1, and the best fit is going to be close to 1, the worst fit is going to be close to 0, and we just lose information about whether it's positive or negative in that situation. So R squared is a different way of measuring how effective this model is at explaining the relationship that we see, but it has a very specific interpretation. And it turns out what R squared actually gives us, because of the way we constructed R squared gives us the fraction of the variation that we see in those Y values that is explained by our model using the X values. So in other words, if I have this model and my R squared value is, say, 0.75, then that means 75% of the variation I see in my Y values is explained by the model. There's still 25% of the variation that's left over that is not explained by my model. Okay. And so this is kind of telling me what that says. Okay, if this is, say, the predicted value I'm trying to predict, like if you remember the scatter plot from before, I was trying to use protein to predict fat, right? And if this is the distribution of the Y values, my model gives me some portion of that prediction, okay? And the residuals then should tell me, oh, I'm sorry, this is actually the difference from the average, that's why. My residuals should tell me how far from the predicted value in the model that each data point ended up being. And as you can see here, the distribution for the original scaled values is wider than the distribution for the residuals. The residuals basically tighten that window, okay, because I'm using the model to make a partial prediction, and that gives me some information. If it's a great fit, it will give me a lot of information, and this will be tightened significantly. So what I notice is that the R squared tells me how much of that variation in the original values that I can remove by using this model. There's, of course, in most cases, some variation I cannot remove, and that variation is 1 minus R squared. So the R squared tells me how much of the variation in the Y values can be explained by my model, and 1 minus R squared tells me how much cannot be explained by the model and still exists just elsewhere in the data or in the population. All right. So I do want to emphasize the conditions to check, and in fact I have one more to add now that we've looked a little bit more at residuals. If you are running a linear regression and trying to use that model to make predictions, you want to check the 3 conditions necessary for correlation first. So just to recap on those, there's the quantitative variables condition. You need to make sure that the 2 variables you're looking for, your input and your output, are both quantitative. If either one of them is categorical, you cannot use this. So it's thrown out. Second, look for the straight enough condition, and usually the easiest way for us to do this at this stage is to draw a scatter plot. Ask yourself, visually, when I look at that scatter plot, does it look like there's a roughly linear relationship? Okay. Is it straight enough? Do I see a curve of some kind? In that case, I might still find but they're very... very similar. So nothing should be surprising, but of course, as a cumulative exam, there's a lot to cover. And so my suggestion is start early in the week and then work on it over the course of that 5-day period. Now's a good time to go ahead and tell you that we will meet again next week to cover the last module. The following week, which is finals week, we theoretically have a class time, but the way I'm planning to run that is I will hold an extra office hour during that class time.